universe and music. Copyright. Anything related to copyright. If I will just turn it on. Seems to be noisy. So first read about reliability. Complex system involves several components. Complex systems involving several components. Basically, the first thing that came to my mind is about a complex system that has a lot of components. Is a gas system in physics. So in such a case, we describe the behavior of gas or fluid using the probabilistic physics, which is a macro way to observe the group of particle, cluster of particle, or a container of particle, instead of looking at the particle individually. So, or maybe a complex system related to you can imagine a complex system involving several components, like a group of people, and each people has a probability to do some certain thing, and now you are interested in monitoring the group of people by calculating some certain quantity, maybe probability that they all do something together, go to a certain event, organize something, build something. Their productivity is something that is not probabilistic in the ideal case. Okay, a lot of complex system with that we can consider here. It is convenient to assume that the behavior parents are okay, because it's convenient to assume that the behaviors of the components are independent of each other, because in such a case you don't have interaction between the individual and a bit, but um, and then it will be easier to model and to calculate some certain quantity, some probabilistic quantity. This typically simplifies the calculation analysis. Okay, as illustrated in the following example. So in the book, in the book, this is the following example. Network connectivity. Yeah, exactly. A computer network connect to nodes A, B. This example reminds me of a graph theory where you have a graph determined by pair, determined by a pair, determined by a set of E and B, where E are edges connecting the vertex V's. And it will connect to nodes A and B through intermediate nodes C. Right. And prepare the link of I to J. So link failure are independent of each other. So okay, imagine that we have a network of computers and they are connected to each other. They are by links, and the probability of connecting successfully between a node AI and node AJ is a number that is greater than 0 and smaller than 1. So basically, from the graph perspective, you can see that the edge weight here is a probability to link one node to one another, uh, and that weight is greater than 0, smaller than 1. And in this problem, in this example, link failures are independent of each other. I mean, the weight of one edge is independent of the weight of other edge, or generally speaking, they are independent. Series of connection. Okay. What is the probability that there is a path connecting A and B? Okay. So look. This section is talking about reliability. So I guess the example is trying to lead us to determine the reliability of a system. I guess. And in this case, we determine the reliability of the computer network. You check. No, it's not to check, to establish, to estimate if the network is stable, can be used, can be trusted to use. Okay, here. This is the figure. And I should publish this image. Actually, okay, it's not worth the publish. So think of this. The probability that there is a path connecting A and B. Intuitively, it is easy to calculate. Easy to calculate. Path connecting. So what should we use here? Determine a path between A and B means determine the probability of an event where all link are successful. Right? Probably. Simplified version. Typical problem assessing the reliability. Fail. It can fail independently. Oh, so I see. This is a typical problem of assessing the reliability of a system consisting of components that can fail independently. So imagine that a software system that contains multiple components, and they're all connected together. But and you somehow you code it, you program the components that are relatively dependent of each other, and there are probabilities for some component to fail, and if they fail, they are in reality in reality there are some probabilities that they may fail dependently, but mostly they will fail. Mostly they will fail independently if you code the system well enough. But I don't think that we can approach that. That is asymptotic behavior. Such a system can often be divided by subsystem variation. Series 1, 2. Component I is some probability that the component I is This is a series. Multiply. No. And then a series. Multiplication. System succeed. So it probability of failure. So it probability of failure. Okay, let me try to paste it here. It's intuitively it's easy to calculate the system like this. You just multiply to estimate succeed the succeed rate of a link from A to B. You just multiply the probability of each link using multiplication rule, and you can find the succeed rate of the entire path. But there are many paths. And series subsystem, succeed parallel subsystem, succeed parallel subsystem fail. Parallel subsystem failed. I don't quite understand. See. 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 Hmm. Series. So this is easy to understand. P series of subsystems to see if it's easy to understand. Parallel. I don't quite understand the. Okay, so I may ask. probably like that. Okay, it can draw you a network. ACB. ACB. There's an F connect to B. No, F, D connect to B, and F connect to B. Anyway. The entire set. Parallel system. Subsystem. What is a subsystem? Subsystem united. External time is a series. Oh, my bad. Oh, yes. So you have a two link, parallel link. Oh, system bell multiple. So this is how they construct a probabilistic model. So hmm. The thing is, this it would be easy to understand. On all path L, all path L. Ah, yeah. So suppose that there are multiple paths from A to B. They are parallelly, they are parallelly linked, connected. A B A B A to B A to B A to B. For the system to fail, you have to fail all the paths. So we need to calculate the probability of the all paths. One link, one connection, one path is succeed, is successful, then that's the case where the system is working properly. Well, succeed, yeah. So you more take one as this. Okay. Well, after this problem, what do I see? To calculate the probability. Calculate the probability that there's a path connecting A to B, no matter there's one path or any path, at least one path. You can imagine there's at least one path. Probability. one path working perfectly. That means all the links are connected successfully. Calculate. So you have to calculate the probability, the success probability of each subsystem where the subsystem is unit. Subsystem are unit. I mean, they cannot be breakdown. It cannot be broken down into smaller pieces. For example, you have a series, you have a subsystem of series, then a series cannot be broken down to any. The unit okay, so determine the unit here. You can break the system down to the unit of series or the unit of parallel link. Like if A connect to B, connect to C, connect to D, bias series, and that's a subsystem you can consider. But now suppose that there's a node E where maybe C connect to E and E connect to D. In such a case, you have to break the system down to two other subsystems, and these subsystems are unit. A, B, C, D, and C, E. And calculate the probability. Succeed probability of the bigger system. So using these formula. This one for the subsystem parallel link. And using this formula for series. No summation. Think of this. So let's think about this in terms of computer programming. Maybe a network of n components. They are series connected and parallel connected. Find the path, find the probability from one path, or from one node to another node. How of programming. And in this system, you have to determine which is series and which is a series or which is a parallel subsystem. Okay, may I ask it? In graph theory, suppose for a prop where we probability to AI and AJ in the exact solution. So you have a exact solution, exact algorithm, inclusion, exclusion, sum of disjoint. Monte Carlo recursive algorithm decompose the network, so smaller subsystem. Of course, that's the brute force idea, solving them recursively and combining the result. No, I don't think this can be efficient for certain types of network topology. Right, for search, yes. Explore the network from we have to each A star this algorithm by shorting path between two nodes. Short this path between two nodes. Nah, I don't think this can be useful. Polynomial. Computation intensive but provide exact solution. We don't need exact solution, we need an exact solution and the simplest complexity using multicolor. Wow, really? Okay, so we will have the weight of each edge is p of each edge, ij is pij. This probability is smaller than 1, greater than 0. Add node from, you have a node. Okay, this is the construction of node using network X. X, a Python library for supporting calculation with graph. You can do a lot of things using this library. But okay, in this case, they create a graph of n node. They add the node. They add the edges. That's path check. Okay. Check if AI connected. Okay. But it's what success. The idea of Monte Carlo connectivity is it just provide a random sample and in this case random state of the graph. HS success count. Like counting. Beautiful. What an idea. This idea is wow. So okay, they in this case, in this algorithm using the multicolor simulation, the ChatGPT tried to express the probability to connect two nodes to random nodes to any node to random nodes, representing the connectivity by just providing a sample of randomness. Provide like if maybe you can imagine if A and B are linked successfully together with the probability of 0.8, and so the representation here is for five connection. For five connection, you will have four successful. The idea is pretty cool. You will get the what? You will get the probability that one connection is one. Okay, let's try. I'll try this one. Personal. Yeah, exactly. So, it network X. Okay. Got here. So this is the older version of network X, but I don't want to update it, and I forget how to activate this. Maybe gonna activate that exactly. Have a look at the notebook. Here we have it. Here we have it. Sample using network X. Maybe try to create a new notebook. Reliability. System of a network. And here you have this one. Edge. For example, you have let's try A. Let's map A is 1. A is 1. B 2. C 3. Hold on. Just a minute. Just a minute. Just a minute. Just a minute. How to in the setting. properties. How to edit this video? Ah, okay, I see. But I cannot change it. Maybe I need to off it. Nah, no. Anyway, this is much more interesting. I think this will be working. ABC. We have a 5 note. 5 note. See ABC. So the graph A is connected to C. A is connected to C. C connected to E. Okay. Um, C. E connected to B. A connected to C. C connected to F. C connected to F. 3. 6. F connected to B. 6 to 2. And A is connected to D. A connected to D. A will be 4. D connected to B. 4. 2. Match probability 908 1 2 no 1 3 3 CD CE. Please 9. 4. Let's see. 420. Okay. Oh well. Okay. 151 AI now. Need to connect. Calculate probability connecting A to B successfully. Okay. Run this. Oh, my bad. What is this? Probability as what? What's wrong? Here 2 6. As prop. Ah, my hand is painful. As from the probability as prop smaller, and you add the edge. What's wrong here? 1 3 if 4 2 4 4 2. Unlike edge prop. Edge prop. This is 2 in line it's wrong and calling to this maybe and it's get things wrong here, you have to debug. Okay, let's try this finish. We don't care about this so far. Don't care about this so far. One 3 1 4. Okay, why are there a lot of edges? Ah, okay, I see. Because his n is gonna try n with 1. 1 3 1 4. Okay. Okay, 6. Okay. 5, 2, 6. Two, 6, 2, 4. Wait, 2, 4. 4, 2, 2, 4. Okay. Totally, we have 1, 2, 3, 4, 5, 6, 7, 7 edges. 1, 2, 3, 4, 5, 6, 7. Yeah, alright. So it's the thing is it confused 2, 6 with 6, 2. Oh, okay, I see. I copy paste this. No, it's consider. Okay, let's try to copy this. Seems to be promising. No, we don't need this. There's prop to both sort. Really? So basically we just sort them for convenience. 6. 2, 6. So 5. Seem good. Because n is 10,000, so it's oh no, my bad. And the result is nearly true. It's hard to confirm because the correct result is 0.7. Maybe increasing this can help. How long does it take? It will take and oh my god, this is not and this is yeah, approximately quite long. How many? 10 million. Random edge. At edge. The color. Beautiful. Beautiful. That's a multicolor, but it's like an inclusion, exclusion. It's exact probability of connectivity. Computing all possible paths. Their intersections. That's like quite long, huh? I have to create a graph. Okay, maybe 1 million. Takes really long time. Try this. Much faster. Okay. Yeah, correct. What a beautiful, beautiful simulation. When you deal with probability, you can use a multicolor to simulate your system. But this method is what's how to say? This method is only good for finding the range of, of your result, determine how your result should be closer. It's not good for finding exact solution. It cannot be used to find exact solution, exact result. Mm, very nice. And it's so too slow. Uh, how the algorithm can be rich. This algorithm can be adapted to count the edge probability. Explore can be rich. Got this path. Now the extra algorithm, extra for finding the show the probability in 2 nodes. They have nothing to do with probability. Recursive. Try recursive algorithm because in such a case we can store the result into no actually we cannot. There's no repeating, no repetitive computation in this approach. How about I like this. So in this case, it fixes the problem of distinguish uh, one action is reverse. Mm, I, this is no, please just and recursive. Try this one. Let's see what we can find. Wrong. Maybe something we don't go into much detail here, but the result is wrong. Incorrect. Recursive. And I don't think this works too. Maybe this is too complicated for Lamau. Okay, let's check the edge. Same result for these, but it's get wrong somewhere. Let's see. Visited with none. Visited with set start and return. Okay. Total. Okay, because if your neighbor is not in visited. Start neighbor prop at not tuple. Okay. Plus recursive subprop. So it calculate what does it calculate here? Recursive. Start neighbor. Probability, if probability, so multiply the probability of the edge. What? Uh, Are you sure about it? Neighbor. Hmm. Okay, you may use this shit. Hmm. Something is not okay. Try this. Okay, we have the graph here. Holy shit. Very bad drawing. Very bad drawing. Or maybe I am bad in configuring. Okay, but whatever. You actually I want to drag number two. Number two. Um, it wants to multiply this multiplied by this. Hold on. Always start with uh, a start, which is 1 and 2. This multiply by this, multiply by this. Neighbor is not. Where's the end? The neighbor. Hmm. Neighbor in what neighbors? Hmm. Neighbor. That. So you can find a neighbor here. Neighbor here. Okay. This neighbor. Neighbor. Profitability. We got extra. We prop with the other neighbor. And you find a neighbor. We get 3. Get this. Neighbor to this. Prop. Prop. Multiply by prop. Multiply by prop. Hmm. I don't think this is actually we can calculate this. But no, we cannot just add it here. Total neighbor not visited, neighbor here, neighbor here. We have a 2 neighbor. Total prop is here. Add. Yeah, adding is alright. And we add the properties. Return so look at this. And uh, look at this. No, 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 no. So Facebook. 3 neighbor 1. What? Why neighbor 1? Okay, that's neighbor 1. That's what we define. But we only care about stock print and neighbor. Okay, let's print the edge. Okay, beautiful. In such a case, we have 1 3 is considered 3 5 5 2. Yeah, correct. And then that's another neighbor. 3 6. 6 2. 1 4 4 2. Why is it not correct? Get the result. Seems to be intuitively correct, right? But in fact, it omit something. Just adding. Yeah, that is exactly what it. But this is not how you calculate the probability of success, because in here you or is this not correct? Because we are considering this is the probability all links are connected, not there is a connected. Yeah, you can understand why this is wrong. Okay, stop here. Let's have the breakfast.